Hello class, welcome back to Introduction to Material Science Engineering. Today we will be talking about the use of phase diagrams. Phase diagrams are exclusively the province of thermodynamics, which means that everything that they predict for you only happens when your system is at equilibrium. This becomes important when we talk about processing and heat treatment because quite often we will deliberately deviate from equilibrium in order to prevent equilibrium structures from forming. But when you look at a phase diagram, whatever the type, you have to remember that what that diagram predicts will only come about if all of the processing changes, such as changes in temperature, changes in pressure, changes in composition, are done very, very slowly, such that all of the material processes that keep composition uniform can keep up. And in many cases that can be achieved by very slow cooling in a furnace, slow pressure changes, mixing components very slowly so that heat can escape, etc. So for our purposes, for heat treatment and metals, that will usually be accomplished simply by cooling slowly. But as we get into Chapter 11 and we start talking about non-equilibrium phase transformations, especially in steelmaking for hardening and the martensitic transformation, we'll be sure to point out what happens when you cool quickly or slowly. But today's discussion, slow cooling, all equilibrium. Okay, we have a passel of new terms to define here, all that concern themselves with what we call phase equilibria. Some of these you may have touched on in your chemistry classes, but we're going to go over them just to make sure. Phase equilibria will effectively be concerned with what we call solubility limits. And you saw a little bit of this in our discussion of solid solution alloys, both back in our chapter on crystalline defects, and also with respect to solid solution strengthening in our chapter on strengthening mechanisms for metals. So just to drop back a little bit, we're going to define a solution as a solid, liquid, or gas which has only one phase, not a mixture which can have more than one phase. So basically it's a bit recursive. So a solution will typically be clear, it will be one component dissolved in the other. So we'll start out with a little example that everyone's probably familiar with, sugar and water. Everyone knows that sugar will form a solution in water, a syrup. So it's not cloudy, but that you can reach a solubility limit by either dumping too much sugar in or by cooling it down if you've already dumped a lot in and maybe at high temperature. So we'll define the solubility limit in this sugar-water case as the maximum concentration of sugar for which you don't have any sugar precipitating. And this can be generalized to be defined as the maximum concentration for which only a single phase exists, no matter how many things you have dissolved. You can have one or two things dissolved in another. So you could have multiple solutes in a given solvent. And the solvent in this case is usually defined as simply the majority phase. And again, you may recall having heard that from our Hume-Rothery solid solution rules back in solid solution defects and alloys earlier in the course. So looking back at our sugar-water phase diagram, we have composition on the x-axis, and this is weight % of sugar. So over at the origin, where it says water 0, that's 100% water, all sugar-free. And then completely over on the right, you have 100, where it's all sugar, so it would all be a solid crystal of sugar. And then varying proportions of those two as you go across. And then temperature in degrees C on the y-axis with 100 degrees C up at the top, so that's a boiling point of water if nothing's dissolved in it. So if we go from left to right, we're increasing the amount of sugar, and if we go from bottom to top, we're increasing the temperature for a given ratio of sugar to water. And you can see there's a dividing line there in the light blue, the solubility limit. So everything that is sort of above and to the left of that would be a liquid solution with two components, water and sugar, water probably being the solvent and sugar probably being the solute. And then over on the right-hand side and a bit downward, you have two phases. You have a liquid, which will have both water and sugar, and then a solid, which in this case is going to be pure sugar, but in other cases isn't necessarily going to be a pure compound. So we could ask ourselves a question: what is the solubility limit for sugar in water at 20 degrees C? Well, to find that out, we could use this diagram by simply drawing a horizontal line, which we just did in the animation there, at 20 degrees C, and seeing for what composition on the x-axis it intersects the solubility line. And we look down, you can see the vertical line that was just drawn, it's 65%. So you can dissolve up to 65 weight percent of sugar in water at 20 degrees C. If you go more, you're going to end up with two phases, a sugar-water liquid, and then an all-sugar solid in equilibrium with one another, dynamic equilibrium. So, and there's the answer in written words. So we can put forward a couple more definitions here, define a couple more terms: components and phases. So you saw from our sugar-water diagram, we were looking at water and sugar as being two components of the composition of the overall mixture, which could then be a solution, or it could be a mixture of multi-phase solutions. So we define components as the elements or compounds which are present in an alloy or any kind of combination of solutions and phases. So in the case of sugar and water, water was one component, sugar was another component. If we have, say, a binary alloy, an aluminum-copper alloy, aluminum would be one component and copper would be another component. Now, when we mix these components together, sometimes they'll form a solid solution or a liquid solution, and sometimes they'll form multiple phases, each of which will be a solution with a different composition. We define a phase as a physically and chemically distinct material region. And I'll add, these have a boundary. In a precipitate, for instance, in our sugar, the boundary was the boundary between the solid sugar and the liquid syrup mixture. In the case of this copper-aluminum microstructure that you can see here, which is probably at fairly high magnification, at least 1000x, you can see that the optically distinct regions are multiple phases in the microstructure that have different compositions. The alpha phase is very likely to be an aluminum-rich phase, and the beta phase is probably an ordered intermetallic of aluminum and copper that'll function a bit like a ceramic. So they have distinctly different compositions, and they definitely have a boundary around them. Okay. Going back to our sugar-water solution, we're going to start looking at the effect of changing what we call state variables. If you've taken some mechanical engineering classes, you might be used to hearing about state variables in terms of enthalpy and entropy. From your physical chemistry courses, you're probably used to hearing about state variables, again, in terms of enthalpy and entropy, but maybe also Gibbs free energy. Ones that are more common are temperature and pressure, and in this case, composition. If you're a chemist, you're probably used to hearing about the more general state variable for composition as chemical potential, or the change in Gibbs free energy with number of moles. Phase diagrams concern themselves with which phases are stable for a given set of state variables. So typically you'll see phase diagrams that describe which phases are present over a range of concentrations as a function of temperature or pressure. In most material science processes, pressure is equal to 1 atmosphere. Most of your factories run at 1 atmosphere here on the surface of the Earth, although of course if you're using a hydroclave or an autoclave, say to do a cure on a composite, you might well run into much higher pressures. A geologist will definitely end up looking at very high pressures for the phase stability of their minerals and rocks, especially down in the mantle. But for the purpose of this course, we will be assuming 1 atmosphere of pressure and then only looking at the effect of 2 state variables, temperature and composition. We won't even get into chemical potential, which is a little bit more complex than composition. So 2 state variables only, temperature and composition. If there's an exception to that, we'll point it out and then point out how analogous it is to temperature and composition. Okay, getting back to our sugar-water phase diagram, we can look at how altering the temperature can change number of phases as well as what is stable. So we're going to do a little animation here. So we're going to look at the effect of heating up about an 80 degree C temperature increase, starting at 20 degrees C with a 70% sugar in water mixture, which at 20 degrees C was a 2-phase mixture. As we increase the temperature somewhere around 60-65 degrees C, eyeballing it, we cross the boundary into a region of the phase diagram which told us that only 1 phase was stable. And certainly that was true up around 100 degrees C. So what happened? We changed from a 2-phase stable solution to a 1-phase stable solution. And on a microscopic level, what that meant was all of the sugar precipitates, the single-phase sugar particles that were probably about 100% sugar, maybe had a tiny bit of water in that solid, dissolved. And now we had a liquid that was water and sugar that had a higher concentration of sugar than the liquid which had been in equilibrium with the solid sugar down at 20 degrees C. We can do the same thing by changing composition. So we're looking at another animation here. If we have a path from B to D, so B was our orange circle at 70% sugar and 100 degrees C. If we were to add some sugar, so we went from 70% sugar to 90% sugar, but we kept the temperature the same. So we only changed 1 state variable at a time. We would go back into our 2-phase region, because somewhere around 80% sugar at 100 degrees C, we would exceed our solubility again. And now we'd be back into a 2-phase region, which had, if we look at the purple dot, by adding sugar up to where our average composition of the whole mixture is 90% sugar, we'd now be split between a bunch of pure sugar precipitates and some syrup liquid that had somewhere less than 80%. But the total of those, based on the ratios, would add up to 90% for the overall mixture. So we can go from single-phase regions to 2-phase regions and back by changing either of the state variables prescribed on the phase diagram. If we changed another state variable, say we put this solution into a pressure cooker and we changed the temperature, changed the pressure, this entire phase diagram would then not apply. We would have to be looking at a phase diagram that represented the pressure that was being given to us by our pressure cooker. So when you look at the state variables that are shown on a phase diagram, there will usually be a note, if you're looking at one generated from someone else's data, which other state variables are assumed and their values. So like I said, not knowing anything else, you can assume that anything in this class is going to be at 1 atmosphere of pressure. But if that ceases to be the case for whatever reason, you can no longer use the values coming from your phase diagram. A word of warning. Okay, so stepping back and looking at a very classic system in metallurgy. This is the copper-nickel binary phase diagram. This is, if you remember from our discussions of solid solutions in defects and solid solution strengthening, this is a noteworthy system in that these two metals are completely soluble in one another in the solid state. So they don't ever form 2-phase solution. They stay single phase all the way across the phase diagram. And now we can actually see this. So we have weight percent nickel on the x-axis in this diagram. If we're over to the left where it's 0, that's 0 weight percent nickel, which means 100 weight percent copper in this case. And then over to the right, no copper, 100% nickel. And you can see there are no phase boundaries until you get to 1100 degrees C, and then all you have is the liquid solid from melting whatever composition we have. So in the solid state, we don't form any different phases. It's all the alpha face-centered cubic solid solution. Now we can get a liquid phase if we raise the temperature. If we have pure copper, we're going to get a liquid starting at probably right around 1100 C based on what I'm seeing on the diagram, and at about somewhere between 1400 and 1450 degrees C if we have pure nickel. Now in between that, the onset and completion of melting or solidification changes depending on our composition. So we will have a two-phase region, liquid plus our alpha solid solution, depending on our temperature and our composition within that region. So we'll do some examples with the animations on this diagram to take a look at how that works. And just a couple more words from the slides here. As I mentioned, this is called a binary system, and that means we have two components, in this case copper and nickel. Our sugar-water system was also a binary system because it had only two components, sugar and water. If this were, say, a three-way alloy, say we had copper, nickel, and aluminum, that would be called a ternary system, and 4 would be a quaternary. Those are much more complicated diagrams that slice usually at single temperatures and use a triangle or more complex arrangement to show phases. We will only be working with binary systems in this case. And as we mentioned before, we have two independent variables, temperature and composition. We're assuming pressure is 1 atmosphere. Okay, so we're focusing on it on a clean slide here. So binary, two components. Because we don't have multiple phases in the solid state, we only have liquid and then a single solid phase. This kind of phase relationship or phase diagram has a special name. It's called isomorphous, which literally means the same form. So it's another way of saying it's single phase across all compositions. Okay. So now we're going to look at what happens in that two-phase region that has liquid plus our alpha face-centered cubic solid solution, because that is a two-phase region, and we have to know how to walk our way around two-phase regions in terms of how much of each phase is present, and then what's the actual composition of each of the two phases that are present. So we're going to again have some animation. We're going to look at 1100 C, and we're going to look at a 60 weight percent nickel overall composition. So that would be shown by a single point on the phase diagram, the sort of pink point that you can see there, point A. So at that temperature and composition, we have one phase. It's a face-centered cubic solid solution. We'll call it alpha. Typically Greek letters are used to indicate phases, by the way. So you'll see liquid for liquid, and then alpha, beta, gamma, delta is the typical sequence to name your multiple phases. Okay, and we'll look at another scenario where we have 30 weight percent nickel and a little hotter, up at 1200 degrees C. And you can see, unlike A, composition and temperature combination B is in that two-phase region. So we're zeroing in again on our 35 weight percent nickel, which we started seeing was in the two-phase region in our previous slide. We're going to take a look at this composition and cool it down and see how the phase relationships change as we go from it being all in the melt to being in the solid. So we start out all liquid. We have 35 weight percent nickel, and we've got a temperature of 1320 degrees C, and that's labeled as point A on this diagram. They're kind of in the upper center of the diagram at TA, 1320. all liquid. It's up in the all liquid phase portion of the diagram. So there's the composition. The overall composition in phase diagrams is usually referred to as C naught or C sub 0, and that's the composition of the whole alloy, which will typically be different than the composition of any given phase. But because there's only one phase, everything's liquid, that's also the composition of the liquid. So we're going to cool it down. We're going to cool it all the way down to 1190 degrees C. Well, we went from one single phase region straight through a two-phase region into another single phase region. So we're at a cooler temperature, and rather than having liquid, we now have all solid, and it is, since it's all one phase again, and we made that change at equilibrium, that has an average composition also of 35 weight % nickel. But rather than being a liquid, it's C sub alpha, meaning that's the composition of the alpha phase. And that's the only phase we have. But what if we're right in the middle? What if we stopped our cooling at 1250 C like we saw on the previous slide? Well, now we're in that two-phase region. Although the overall composition is 35% weight % nickel, the alpha solid and the liquid that are coexisting in equilibrium, there's two phases, they're not the same composition, and neither one of them is 35 weight % nickel. So if we want to see what the composition of the alpha and the composition of the liquid that are present, we use what we call a tie line. So we draw a horizontal line across that two-phase portion of the phase diagram, and we look at the portion that is touching each of the phase regions. So we looked over on the left-hand side of our heavy black isothermal tie line, and we noticed it touched the liquidus, the boundary between the two-phase region and the liquid region, and the composition corresponding to that touch point is 32 weight % nickel. So that's the composition of the liquid present for a 35 average overall weight % nickel alloy at 1250 degrees C. So I bet you can guess what the composition of the alpha solid that's in equilibrium with that liquid is. We'll do the animation. As I'm sure you guessed, it's given by where that same tie line touches the solidus, or the boundary between the two-phase region and the alpha solid, which happens to be at 43 weight % nickel. So these add up. It's no surprise that these are on either side of the original composition. In order for the overall composition to be 35 weight % nickel, if the liquid is a little bit deficient in nickel and more rich in copper, the solid's going to have to go the other way. And they will be actually related by the weight fractions of the two phases, which is what we're going to get to next. So we now know that at 1250 degrees C and 35 overall alloy weight % nickel, we will have alpha solid solution of copper and nickel in equilibrium with a liquid, and we know that the composition of that alpha is 43 weight % nickel and the liquid's 32 weight % nickel. But how much liquid is there relative to the amount of solid? Do I have more liquid present, or do I have more solid present? That could be important for processing, whether maybe I'm solidifying quickly enough, or can I move my mold? Well, the tie line can tell us that too. So just a quick review here, remembering that we cooled down from TA, where we had all liquid, and if we had gone all the way to TD, we'd have all solid. We can use the ratio of the tie line regions to tell us how much liquid and how much solid we have. So the amount of the weight fraction of liquid, and in this case it's a fraction based on just two phases, liquid and solid, the weight fraction of liquid is the portion of the tie line labeled S over the entire length of the tie line. Likewise, the amount of, or the relative fraction, weight fraction of alpha phase, not composition of alpha, but the amount of phase alpha with respect to the liquid, is the length of the R portion of the tie line, that horizontal tie line over on the diagram, divided by the total length of the tie line. And this should make sense, because if your overall composition is closer to the liquidus, you have probably more liquid present, so the fraction would be given by the opposite side of the tie line. So it's a little bit opposite intuitively depending on how you look at it, but when you are looking for the relative amounts of two different phases that are present, you ratio the portion of the tie line going to the opposite phase boundary over the total length of tie line as a general rule. And then you pick the composition of each of those phases based on the composition of where your tie line intersects each phase boundary. So there's two distinct ideas to get when we're talking about a two-phase region on a binary phase diagram: the composition of each of the two phases present and the relative amounts. So you use that fraction of the tie line to get the relative amounts, and then you use the intersection of the tie line with the phase boundary areas to get what each of those phases is composed of. Okay, and that division of the tie line to get the fractions of each phase present is called the lever rule. And again, that just simply refers to the fact that we are looking to the length from the overall composition to the opposite phase boundary intersection to get the relative amount of each one. And you can think of it as being a bit of a teeter-totter. So you can just take a look at that. And by the way, the tie lines, needless to say, because they are drawn at a single temperature, they are isothermal. So if you're used to thinking in terms of contour lines on a diagram, these are isotherms. So single temperature lines, and they're always horizontal on these binary phase diagrams. So just a little picture of the lever rule to get our relative amounts of phases. You can see that the R and the S that we've divided our tie line into are denoting the relative fractions of alpha and liquid, and they have to balance composition versus relative amounts. So there's another way too. It's kind of a derivation of the lever rule there. The easy way to remember it is just simply to take the length of the tie line, and the relative fraction will be the length of the portion between the average composition and the opposite phase boundary. Okay, we'll do another example here, but we will also look at what's happening microstructurally. So far we've only concerned ourselves with what the composition, well, starting with how many phases are present, where the boundaries between single and multi-phase regions are. So do we have one phase or two or more? Then we've looked at what are the compositions of the phases present, and then we've looked at the relative amounts of the phases if we have more than one. So now we can look and see, okay, what's going on inside the microstructure? We're familiar with the idea that we have grains, and if we have another phase, it'll probably want to precipitate on a grain boundary, and it'll form its own grain, and it'll probably have its own crystal structure. Some will be FCC and BCC, and we can get different things dissolved in each one of them in the interstitial positions or as solid solution substitutions. For instance, our copper nickel is definitely a substitutional solid solution. It's not interstitial. So we're going to use little circles as sort of schematics of what's going on in the microstructure, and these evolved over the years of optical microscopy, where we could actually image what was going on in the microstructure after the fact by rapidly quenching samples and then doing optical microscopy and taking pictures. So we're going to show a series of circles that would be basically representational microstructures as if you had done optical microscopy on the microstructure. So we're going to stick with our 35 weight % nickel, copper nickel binary alloy. Right now it's in the melt, so you can see a big green circle that is representing looking at a magnified picture of just liquid metal. It's all one liquid solid solution. So when we cool that down to B, we hit the liquidus, and we start precipitating out alpha solid in the liquid, and so we can now see those little particles of alpha floating around as little blue dots in the liquid. The liquid still has an average concentration of 35 weight% nickel, and based on its position over on the solidus, where that horizontal blue tie line hits the liquid plus alpha boundary line on the alpha side, that corresponds to 46 weight% nickel. So those little tiny initial precipitates that we formed when we first started to solidify that alloy were far richer in nickel than the original overall liquid composition. So that is following that solubility phase relationship. So we cool a little bit more, and those precipitates grow. So our alpha solid is still floating around in the liquid, and it's growing. And you can see that the difference in the composition of the liquid versus the average composition of the solid, it's now growing apart. So the liquid is effectively becoming more enriched in copper. Now it's only 32 weight% nickel. It started at 35, so it's lost some nickel. Well, that nickel's been picked up by the precipitates, which are getting, on the average, they have a little bit less nickel overall, but less than those initial precipitates, but still quite a bit more than the average. So at D, we are getting close to being done solidifying. We definitely have more solid than we have liquid. Now the composition of that solid has pulled closer to the average overall composition of the alloy, and that shouldn't be surprising because now the solid is practically the majority phase. It should be close to the overall composition, and the liquid has been severely depleted of nickel. It's much more heavily enriched in copper now. Effectively, you can think that all the nickel has been sucked out of the liquid and deposited into the solid, leaving a very copper-rich liquid behind. Well, eventually we solidify completely, and since we're at equilibrium, the composition averages out. We get really fast diffusion, and so we always stay at a uniform composition, even in the solid. And so now we have all solid. The grains have now, the precipitates have grown together. We've formed grain boundaries between them. So we have a polycrystalline solid there that has one phase. It's all alpha, and it's the same composition as the liquid we started with. So that is a solidification sequence of a single phase, completely solid solution. Okay. We mentioned that this is the case, or phase diagrams only apply if we cool slowly and we keep everything at equilibrium. We're going to take a look at what happens if we cool too fast. And in this case, too fast literally refers to whether or not diffusion in the solid can keep up with the rate of deposition of new material from the liquid, and what will happen if it doesn't. So in this case, cooling at equilibrium has a very specific definition in reference to a mass transport property that we've already studied, namely solid state diffusion. So this is kind of back to that Fickian diffusion concept. So in this case, what we're doing is diffusing copper and nickel back and forth across our growing grain, because the new material that's depositing, we saw here from our phase diagram, is not the same. Every new layer of solid that we add to those precipitates has a little bit different concentration. It's a little bit richer in copper and poor in nickel. Well, for that final solid, for all the way across that grain to have 35 weight% nickel, we have to get all that nickel rich, the nickel atoms and the nickel rich original core out to the outside to mix with the copper-rich material that's coming down last, that copper-rich liquid. So again, that has to happen by diffusion. So if that diffusion doesn't keep up, we end up with a non-uniform composition across the grain. And this little animation will show you a schematic of what happens in that case. So we're starting with our equilibrium cooling. So if we have a slow rate of cooling, we end up with a uniform composition across our grain, and it's shown as just a big blue grain blob because it has the same concentration. So the color is representing the weight percent nickel in this case. If we cool fast, we're going to end up with nickel-rich core and a copper-rich boundary. So again, the first solid to solidify is 46 weight percent nickel, and then each new layer has less and less nickel, which is being represented by a lighter and lighter color. So in this case, darker color means more liquid. So it's only the last alpha to solidify that has less than the average composition, and it would have to be less because the average has to be 35. So if the core has more, the outer edges of those grains near the grain boundaries have a lot less. Before we go on to eutectics and lamellar structure, an important consequence of having that difference in composition across grains in one case is that we can have a variation in melting point. If we back up to our binary phase diagram and look at it all the way across, backing up here, you can see that our copper, ignoring the animations for the moment here, copper has a much lower melting point than nickel. If we cool quickly and we have a nickel-rich grain center and a copper-rich grain boundary, even if you have an average 35 weight percent overall material, which you would predict to start melting, somewhere just shy of 1200 degrees, if you had a copper-rich grain boundary, it might start melting just a little above 1100. And so if you were planning a thermomechanical process close to what you thought was the melting point, you might be actually performing it above the melting point, and you could suddenly have something splattering with liquid metal in a forging process where you hadn't expected it, and that could be a severe plant safety problem. That used to happen in the early days of steel making and was referred to as a hot short, and was very dangerous in a foundry setting or a hot working setting. So understanding that with respect to processing is very important.